Okay, so now it's being recorded.
Yeah, so welcome to Feza Gürsey Center for Physics and Mathematics Higher Structures Seminar Series. Today is the first talk of the spring semester, and our speaker is Nils Baas from Norwegian Technical University from Trondheim, and he will talk us on beyond categories. So we thank him very much, and please, Nils, yeah.
Thank you very much for the invitation. It's very interesting to talk in this seminar. So it would have been more interesting. We said that Zoom was a great invention, but it would have been even more interesting to visit Istanbul.
Yeah,
I've never been there, but anyway, sometime in the future.
hopefully.
Okay, I'll talk about beyond categories, and this is something that has puzzled me for many years. And today, the notion of higher structures has become a very popular, mostly often meaning higher categories, which I think is a very reasonable and good interpretation of it. But I will argue that maybe one should have an even broader perspective. So when we talk about higher structures, often say we start with the set. Most higher structures are of the form that you can pin them down to a set, looking at the power set, power sets or power sets, etc. So you consider sets of sets, systems of systems, structures of structures, etc. But the point is, this is also a pattern that in biology evolution follows. But evolution also detects the properties of things constructed at one level and use it for the construction of the next level. That we haven't really been very good at mathematics to incorporate. And of course, we have the notion of hierarchies and trees, all excellent examples of higher structures. But let me write down here on the slide the hierarchy of jokes. And let me offer you a Scandinavian adaptation of the hierarchy of jokes. So let's say we have a Norwegian telling a very funny joke and everybody is laughing. Then we have a Dane telling a Danish joke about a Norwegian joke. And everybody thinks that's still funny. Then the Swede comes along and he tells a Swedish joke about a Danish joke about a Norwegian joke. Well, still you may smile. But then a very serious Finn come along and he tells a Finnish joke about the Swedish joke, about the Danish joke, about the Norwegian joke. And then it's no longer a joke. Because you can't really keep track of all these things. And the famous author Arthur Koestler, he was very interested in hierarchies, or what I would call higher structures. And he, at the end of his life, he summed up much of his thinking about this in an excellent book, which I strongly recommend, called Janus. And Janus is the two-faced Roman god. And the basic claim, which I think is interesting for us, is Arthur Koestler saying that the human brain seems basically to be designed to cope with three levels at a time, namely the level where we are, the level above, and the level below. And if you think about it, there's some truth to that. And in the hierarchy of jokes, we exceeded these three levels and went to four. Then we have difficulties keeping track of things. And in such situations, I think we need a good framework in which to work and think. And that is one of my motivations for what I later on will call hyperstructures. So this is the motivation. And of course, what I'm saying is, it's just like an extension of, let's say, higher categories, more than an alternative. So let's look at categories and graphs. So in categories, we may pass to higher categories, but still we have morphisms, and morphisms have source and targets. So I would say there are pairwise, they represent pairwise interactions. In graph theory, of course, we have vertices and edges. But also lately, or not so lately, but it has become very popular recently, the notion of hypergraphs, where you extend the notion of edges to a complete set of vertices. And of course, this can be iterated to higher levels. And also, when you look at topology, simplicial sets, ideally, when you think about it, based on pair interactions, you track things down to 2-point edges. So this is the thing I think we could extend. In topology, we also have cobordisms. And for example, in quantum field theory, you orient them and you say that two circles move through space-time following the arrow direction and merge into one circle or particle. And that's fine, but if you look at this pair of pants, cobordism, basically it is, as the figure shows up here in the corner, that it's a bond, I would say, of three circles. And that is the picture I would like to pursue, that of geometric bonds. So let me just put in a few things about categories. Of course, we can extend to two categories and n categories, and by that I mean, in modern terminology, infinity n categories. And one example, just to show that I have contact with with the Earth, is that if you look at the category vector spaces, which we can consider as C modules over the complex numbers, then we could say that 2C is 2 vect. That is vect mod, where vect is the category of vector spaces, and then we take modules over that again. That's what we call 2 vector spaces. This was a definition by Kapranov and Vygotsky, and that John Drongnes, Björn Dundas, and me sort of extended to K-theory and built up some new types of K-theories. At that time, the infinity categories hadn't really been fully developed, and I think there is no doubt that you could extend this to NC, vect mod n, and you get a whole hierarchy of algebraic K-theories in that sense. So also for graphs, you could extend hypergraphs and to hypergraphs to n graphs. And what this really shows you is that we have, in a sense, these societies of structures that I'll call. Also, many years ago, I studied in cobordism theory manifolds with singularities. That's where you have polyhedral singularities, and you peel them off level by level into a hierarchy of manifolds. And this is what gives rise to what's called the chromatic power of cobordism theories. That has become very popular recently in homotopy theory. But again, this is, you look at what I would call NCOB, which is cobordisms or cobordisms or cobordisms. And of course, it takes some technicalities to formulate that in a proper way. So these kind of structures motivate the need to find a unifying concept, giving a framework for handling such structures, where we say higher, whatever you put in the parentheses here, going to what I call hyperstructures. Again, the basic idea is pairs of interactions going into families, in a sense. And let me just, in a parenthesis, note that it was in the late 90s, I was at giving a talk at the category theory conference in Coimbra in Portugal. And this was actually, I think, basically the celebration of Saunders Maclean's 90th birthday. And I mentioned these higher order K-theories at the time. And at the end, I said that, okay, I think we should really go beyond this. And I mean, this was almost like swearing in the church, saying to category theorists that you should forget about source and targets. And I suggested something of what I'm now going to say. And after the talk, MacLean, he came straight up to me, and he was 90 years old, and I thought, now he's really going to kill me. But it was interesting. He said, these things about forgetting source and targets and doing it more generally, that's an interesting idea. You should pursue that. So that was a very good moral support from the grand old man of category theory. Okay, so far. I also gave a talk at a physics conference, and I asked, what is a triple interaction? And everybody said, okay, triple interaction is best represented by a triangle. Okay, where you have the objects as the vertices, and then you have the vertices interaction. And if you really want a triple interaction, that is the area of the triangle. But on the other hand, it's not a true triple interaction, because if you remove one vertex here, it all reduces to a pair interaction. So more genuine triple interactions motivated by topology you find in the middle of this figure. You have the Borromean rings, and to the right, with the same property, what they call Brownian rings. And at this level, they are about the same, having the same property that if you cut one of them, they all fall apart, as opposed to, for example, the simplicity property of a triangle. If you cut one edge, they just contract to a pair edge. So I think these are the kind of interactions we also should include in a general notion of higher structures. So genuine non-reusable triple interactions, we have pair interactions. I think in a categorical sense corresponds to morphisms, and we have higher morphisms. Multiple interactions, like we saw in the Borromean rings, I call these bonds, and we would like also to form higher bonds, similar to the way we form higher morphisms. So if you extend this to the link picture, you see you have, I should say, these, I think I would say, beautiful pictures. I asked them to be drawn, and this was a colleague of mine, Andrew Stacey, who made these graphics, which I think is quite beautiful. So to the left, we have three circles embedded and connected into a three-particle or three-circle Brownian link. Same with the property that if you cut one, they fall apart. But then you could say, and this is how you form levels, that if we take one of these ordinary Brownian links, take three of them, and sort of consider them as circles and put them together, link them up in a Brownian way, then we get the figure to the right. And that is what I truly would call a second-order Brownian link. And we can even pursue this in the graphics to third order. It gets complicated, but that's an interesting construction, apart from just the beauty of the figure itself. And one can ask, like the Borromean rings and the Brownian links, the topology themselves is not so interesting, but the complement has interesting topology. So if you live on one of these links, life is simple. If you live in the complement, it's topologically complicated. And one would like, I have a paper called New States of Matter. It can be found in colors on the archive, where this has been extended a lot. And you would like to have sort of an invariant picking up the degree here of level. But I think no one has succeeded in that. We run some of these classical Homfly polynomials and etc., but the computer cracked down. And I had a long discussion with John Milner after he received the Abel Prize about this. And he thought about this for 3 days, and I said, I can't think of no invariant that would pick up this structure. So it is a deep and difficult problem. So the main prediction in this paper is that to higher order links, in some sense, there ought to be corresponding higher order quantum states of matter, such as in cold gases, nuclei, and other types of many-body systems. And the interesting thing is that these structures, I say this for motivation, is that bromine or Brennan states have been observed in laboratories in, I think it's in Colorado and in Innsbruck, and these are called Efimov states, named after Russian physicist Efimov. And these are cold gases very close to degree 0. So they're very fragile structures. But in quantum systems, also qubits have similar properties. And these are called GHZ states. And Z stands for cylinder. And he received the Nobel Prize in Physics for this last year, or 2 years ago. So a GHZ state is a state of the following form, if you're familiar with bracket notation. Then you can form a second order state like that. And a second order state would involve these 3. So it's actually a 9-qubit state. But this potentially could be interesting in quantum computation. But so far, it's not known how important they would be, but theoretically they exist. Okay, so let me go to simplicial complexes. Many of my colleagues say, okay, there's no need to that. N-simplex would represent all kinds of interactions that we need. And in the categorical world, we say, okay, we have spans and we have multi-spans that would cover this. But the idea is that I'm proposing is that instead of a morphism as a pair of connecting or binding two objects, is that we have a family and we assign a space to it, which could be totally different in structure from what we already considered. So it's more like you have, say, if you have some particles corresponding to these dots, a new space could be a space of like a fluid that binds these together. So leading example again in this thinking, to me, is higher order Brownian links. And again, as I say, one should pursue the search for new invariants. Of course, there is something called the higher order massive products in the literature, but massive products, higher order massive products, just sort of corresponds to extending the length, for example, of the Brownian link, not going to another level. So I think that's an unfortunate notation. Also in gluing, you could have situations in this figure, and these are things that are not, for example, put up in the notion of multispans, where you have morphisms within the same category. Here I would assign a space that would possibly be of a quite different nature. So the notion, I suppose, in going from morphisms to bonds is that of a hyperstructure. And here something I call the H principle, hyperstructure principle. That's if you have a collection of objects, first you observe the objects and detect what kind of properties you have. Then you use these properties, putting them together to new objects. So you have certain things and you make things of things. And then you create levels successively. And also then you may associate states, and you have the problem of going from local to global. And this is a very delicate problem within hyperstructures that requires an extension, I think, at least that's in one of the papers I'll refer to. I wrote an extension of Grothendieck topologies to these contexts. First, you have to revise the notion of a site and then go into topologies. Then you can make sense of these local to global structures. Then composition, and what do I mean by installation? That is, if you have a set, how to install such a structure on the set. So that's a formal framework. And normally, we'd say that, okay, we have a set of basic objects. We look at the power set, and we have an assignment of properties of sets. Then you may say, okay, should this be a category and should omega be a functor? I would say for the time being, not necessarily. Let's just consider it as an assignment. But the properties we would have to wait with. Gamma is this set here of pairs of subsets and properties. And then we have another assignment, think of it as a functor, from gamma to sets. And then you say that, okay, let's now proceed and consider bonds of bonds. And then we look at x1 like this, and we iterate the process. And let me just, I extended this here. So this is from the paper on the philosophy of higher structures, where you see here, yeah, that's actually what I had in the slide. Let me put this together. And here you see how to then extend it. So you iterate this, but it's not a recursive iteration because you measure the properties, new properties at each level, use them to form the new bonds, etc. But also you have what I would like to call a boundary map from level I plus 1 to the power set of level I. And that means sort of dissolving a bond. Or in popular way, you could say a bond knows what it binds. So it's nothing less than if you have a morphism, delta of a morphism is the source and its target. Okay, so that was to make this. Okay, so I've sometimes been discussing this with Dennis Sullivan, and last year I gave a talk in Luxembourg where also Bruno Valette was present, and he talks about operads and properads. So a properad, I would call a one properad. That is, and this is one to the right. That's what my good friend Dennis Sullivan would say, a properad is a hairy thing. That is his intuition. So what is a two properad? Well, a two properad is then a bond of one properads, graphically shown in the middle here, and a three properad then in blue colors. So that is, I think, a very good graphical intuition of how to expand many concepts, for example, properads. Okay, so here in the graphical properads, here are some papers I refer to. They are all on the archive because I thought that was the easiest reference. And let me point out then that a key idea is the use of observables, the properties, the omegas in the definition informing the next level. The graphics is very general and useful, and let's keep in mind that properads, operads, and multimodules, the same graphic applies. So let's look at, again, if we have such a hyperstructure in the sense, in the formalism that I just defined, then you could say that if we have a level I, these are represented by these circles here. The hair represent the properties. We put on the hair, and then we bind them together by red. So that is the graphics of this process. And here you could say that's how you extend it and how to iterate it further. So if you have at one level, you apply delta I, what I call the boundary operator, you sort of dissolve the binding and you are left with the next level things. And here you have then the level above, and here you have the properties, and also what you want to bind at the next level that I call the blue level. Okay, so let me take another example more from traditional category theory, illustrating some of these ideas. Say if we have a category C, and we consider a functor, now a functor, not an assignment, from C up to sets, then we have, I think, what you call the element category, or sometimes it's called the Groton deconstruction, where you integrate P over C, you form the category of elements. I think this is well known to you. So say here we have this category here, we have omega, and then I form gamma 0 is just this, the category of elements over C naught with omega naught as a factor. Then I introduce another functor from gamma naught up to spaces. Again, free sheaf here in this context. And let's see, then we form C1 as the integral of gamma naught, or B naught over gamma naught, and then we iterate this. So at level M, we see that we have these double, let's say, point category constructions. And that is sort of an example of what these ideas I have in mind. And also here you could say what is, yeah, you could think about the nerve construction here in an interesting way, but I won't go into that. Okay, here was, I put this, I mentioned Brownian rings, and there's a notion one could possibly introduce a Brownian complex. That would, instead of a simplicity complex, where you could say we consider a set of vertices, and we pick up a specified sets of subsets that we call the simplices, such that the singleton are there and also the empty set. And let me offer you one example of such a Brownian complex. That's exactly what we see here, where we have 9 vertices, but just these 3 and the whole thing, these 3 circles with 3 other dots, are the simplices. So that is what you see in, for example, second order Brownian links as to the right here. So I think that could be an interesting notion to study, what extending simplicity complexes to Brownian complexes. Okay, so that was an idea. Let me now switch to something, the same figure here, but now in a physical context, namely higher entanglement. So let's say we have 9 rings here, labeled 1, 2, 3, up to 9, and we have 3 trimers, triple particles 1, 2, 3, and we think of them as particles with state spaces, Hilbert spaces H1 up to H9, and for the trimers, H capital I tensor product of these 3 here. Okay, etc. And we have then a total Hilbert space is a tensor product of these 2. So then in physics, especially in, say, our connection with entanglement and also quantum computations, you start with level 1 and you consider pure states. They are just pure product states. Entangled states are sums of products. They are this form here. And they are things that cannot be written as products. Let me just say, yeah. So for example, here, I have an example that if we have in bracket notation a state like this, if it's pure, then there must exist, and you just do a simple linear combination computation here. And you see that it's entangled whenever A, B is different from D times C. So this is interesting, as I said, to extend, for example, these G8Z states and F0 states to second order states. And for these particles, then we could look at entanglements in Hi1, H2, etc. And then as two pure states, we would just take the tensor product of entangled states now, specifically entangled states, and say that two entangled states are sums of tensor products of these again. And this would be metaphorically the same as when we go from Brownian links to second order Brownian links. And this is a figure that I now call 2B33. That was a figure I just showed you. Okay, so now I'll make a big jump, namely illustrate some of my thoughts coming from TDA. TDA is topological data analysis and neuroscience. That's where I have been working recently, and I think there are some interesting things connecting to what I just said there. So let me just recall. We consider brain cells, and each brain cell has a state 0, 1, either it fires or not. So experiments give us discrete time series, what's called spike trains. So if you have 200 cells, you get a vector in R200. And if you have do this over many times, you get the point cloud in Rn. So if you have such a discrete point cloud in R, let's say 200, you'd like to form a space out of it. Then you could use either take correlations between these, use a correlation graph, and then form the clique complex, or you could put balls around each point, let them expand, and then form a simplicity complex out of that. But that would depend on both the correlation and the radius, so there's a notion of scale involved. And this is the theory behind what's called barcodes in TDA. So we'd apply these to various types of cells. HD stands for head direction cells, where you have a cell, it's firing basically in one specific direction. So its state space is a circle. Then you have grid cells. They fire at the vertices of a hexagonal lattice, where I've just picked out 4 vertices here. And it turns out that the state space is a torus. That is a non-trivial, both theoretical and experimental result. So what you do in neuroscience or in brain research is that you do coding. That's, you have a rat, for example, moving in space, and you record when it's moving, you get these spike plates. Then you have the inverse process of decoding, that you take spike planes and want to find out how is a rat moving. That is really a form of topological artificial intelligence. But the points on the torus, they represent collective states. Actually, in the notion I introduced, I think of them as bonds. So all the points on the torus are needed. If you puncture, take away one, then of course, topologically, the torus falls apart. So this is an example how these structures emerge in topological data analysis of brain cells. So just as a digression, since I had these slides around, here you have the brain, here you have hippocampus, and around the hippocampus you have entorhinal cortex. So head direction cells and something called play cells, they fire in the hippocampus, entorhinal, the cortex is this around. So these are very deep structures in the brain. And a play cell fires at one specific point. Now, the rat is moving in a box. The grid cells, they fire, one cell fire at all these spaces. And you see, these form hexagonal lattice, as you see here. And these are heteroaxial cells. And these grid cells were discovered by colleagues of mine here in Trondheim that I've been working with in order to detect the torus state space, and the detection of that is what they were awarded the Nobel Prize for in 2014. So here I'm also in the laboratory with Majbert Moser, one of the Nobel Prize winners. But what is a brain? It's a collection of neurons, certainly, also an organized collection of neurons. I would claim that based on the evidence I've seen, it's a hyperstructure of neurons. What do I mean? So we have field theories in physics, but I think along the lines I've been building up to, we also could talk about a neural field theory. That would say if we have a nested collection of neurons, then we could associate state spaces to these levels. So at level n omega going to s omega, and we get such an assignment. I say assignment, I'm not talking about functors yet in this context. And that would say that, okay, these decomposition of brain cells, they call them actually modules. That's a little bit confusing. So these are physical neural modules of brain cells, and they're built up such a hierarchical fashion, and then you want to assign states to them, and they are built up like that, almost like in a hyperstructure. And so it's in a sense that morphologically you have a level n omega, and further decomposition, you divide it up, and that's coding. Here you have decoding, you go from states at the level k to k plus 1. That's where you sort of predict behavior. So that is going from local to global. So let me recall. Coding is going from global to local, and decoding is going from local to global. So this means that if you can build such a hyperstructure theoretically, and we have a model for that, at least for 2 levels, which is works surprisingly well, that if you code in what, say, 200 nerve cells, how they fire, you can predict basically the way the rat is moving. So that is an example of what I would call a topological neural field theory. But now, let's go to representations of hyperstructures. We know from topological quantum field theory that if we look at the cobordism category, a field theory is basically representation into the category of vect, Hilbert spaces, or some other algebraic category. And recently, the most popular development has probably been Baas, for example, the work by Stotz and Teichner, is that you take 2 cob and represent it in the category of bimodules. But even when you want to extend this to higher categories or higher cobordism categories, these are pair things. Bimodules are fine. So you would extend to bi modules. But if you look at higher cobordisms with singularities of bonds, geometric hyperstructures, where you do not have this pair setting as you have in an ordinary cobordism theory, you like to take this geometric hyperstructure, represent it into an algebraic hyperstructure. But what should this algebraic hyperstructure be? That is, I think, a challenging question. So let me just sketch some ideas here about multimodules, where we take and go from morphisms to bonds. So the idea is, say, a suggestion, we have bimodules, we could extend to trimodules, 4 modules, etc. And then we could combine these level-wise. So the question is, would we just ask for pairwise commutative actions of some rings, or go for other and more fancy actions? That's, I think, not yet settled. So bimodule diagrammatically would look like this, and multimodule more like this picture. Of course, the tensor product is a relevant candidate, but there are also other things. And this looks a little bit like the hairy things picture and the graphics I just showed you. So a sketch is that if we have a family, let's say just a family of rings or algebras, acting on some, let's say, an abelian group S naught, then we will say that S naught is a module over this family when we have suitable actions. I formulated this little bit general, so I'm just simplifying it. So at the next level, S1, we take families of modules of S and take an action of some object S1 that we then call an S1 module. And this leads us to a hyperstructure of modules, S script naught 1 up to n, where we also have these boundary maps, where we take the boundary of something at level I plus 1 is simply the modules at the level below acting on S I plus 1. So again, here you see you use obs, that's detecting the action, and bonds representing the collection of the actions. And if you think about it, this extends the pictures that you see in topological quantum theories and also in factorization algebras. So, okay, so yeah, I don't want to spend time on, so stratified spaces, they also, when they're being decomposed into strata, they also form a hyperstructure in this sense, but I do not want to discuss that. Like here, they have, like if you have two spheres intersecting each other, just to illustrate, you have a neighborhood around the intersection set that is a cone type singularity, S1, times the cone on Z4. But anyway, the point is just that if we have a stratified set, we have a hyperstructure, we want to represent it into some algebraic thing, and then to each strata, we will assign algebraic objects in such a way that they fit together to an algebraic hyperstructure. So the idea here is really to look here. I think this is picture is that we have geometry here, not topology. This is a geometric hyperstructure. It could be cobordisms or cobordisms or cobordisms. It could be singular spaces where you have levels of singularities that decompose. And then you want to represent these algebraically, and you start at the bottom stratum or level with some, let me call it M0 modules, referring to the other thing. Then we go to M1 modules, which is modules of M0 mod, and then we climb up the ladder. So this is a bit similar to what we did for vector spaces, where we considered vect mod n, that here we vary for each level. So I think this is an interesting thing that hasn't been worked out in satisfactory mathematical details, is that having a geometric hyperstructure here, formulating this algebraic hyperstructure here, and considering these assignments in such a way that they generalize the Heisenberg picture in factorization algebras, and also the other picture using topological quantum theories. So then, of course, composition of bonds is a basic issue. So if we have two bonds binding these things together, whenever we have an intersection, so this is like target equals source in order to compose morphisms, you would like to compose these. And of course, you could do that. And there are at least two obvious ways. For example, you could just take the union of these, but throwing away the intersection, or you could keep the intersection. Depending on the situation, both could be useful. And also in general, that would give you could do this, you could if you have n levels, you could buy morphisms at level n by gluing at level k. So that's exactly as you glue things in higher categories. And from this simplicial composition, say ring nk, then you could also form the nerve of the hyperstructure and get a topological structure out of it. And I think that could be interesting because there are many hyperstructures that you want to, like in topological data analysis, that you want to study, whose topology you want to study. And it's like a topological friend of mine said many years ago that the only pleasure a topologist could have of a category is to take its nerve. And there's something to it that it is a very useful thing to do in many cases. But I think so. So a composition is of course important, but here it's formulated in a loose way, admittedly, but to cover as many examples as possible, and also what shall I say? Also giving some mathematical flexibility. Okay, so now we come to the more final point, how to relate these assignments to general field theory. As I said, already pointed out that this should combine and extend the topological quantum field picture due to Schrödinger and the factorization algebra, where you emphasize the observables more due to Heisenberg. And I think this scheme could help us constructing new states of matter, as I said previously, higher order entanglements and things like that. So I think there are three levels we could proceed. So first, we have a geometric hyperstructure, and we have, say, an algebraic one. So in some sense, you could make this into a higher category, this also into a higher category, fine. And then we are back into the world that's currently being studied. But I think also there are examples where we go beyond this, that instead of having such a single assignment, we could say that, okay, we have many assignments, that F is just a bond of the families of hyperstructures. That's extension 2. And extension 3 is that, okay, if we have these bonds, these bonds are level structures. It could be part of a hyperstructure of a other kind that I called HIP, and that F, the field theory, would be an element of HIP of the bonds of Hij. That is sort of how I would envision the ultimate field theory. Like here, for example, you could say that, okay, we have an H of hyperstructure particles, one of links, one of Hilbert spaces or algebras, and they are linked or bond together. That's a picture that still to be explored, but I think of some interest. Remark 2, the neural bonds mentioned should also be put into a neural field theory of this kind. And I think especially levels are important in neural field theory, and the use of mathematics are going from, I mean, experiments are basically going from the global to the local, but from the local to the global, that's delegate, delegate, and there we need mathematical tools like what I would say a kind of generalized sites and sieves in the sense of Grothendieck and Grothendieck topology. There's one question that maybe some of you know more about than I do. I mean, extensions of Grothendieck topologies to higher categories. I haven't seen much about that. Few references of some generalized sheaves, but not. So is there, what should I say, an interesting theory of Grothendieck topologies for higher categories? I would be happy if I could get a reference for that. Well, I think, yeah, we may also have time for some questions, and I think that is what I wanted to say. So here are some references. The two first ones are basically on my views on higher order structures, but also you can find references therein. And as a journal's work, color pictures are much better on the archive than in journals. Here are two of the basic papers from neuroscience, and this torus was actually published in, oh, sorry, that's not here, but that was published in Nature last year. And here is another one that's also on the archive called Higher Algebraic Structures and General Figure Theories. That may also be of interest, similar to what I said at the end. Okay, I think that is my message, and I thank you very much for your attention.
Thank you very much, Nils. It was a really, really interesting talk. Actually, your mentioning of Grothendieck topology for higher categories, uh, I also looked around for references but could not find much about that either.
No, okay, no, I think that's true. And in this reference number 2 here, I have a sketch of what is a Grothendieck topology for a hyperstructure, in a hyperstructure. And that would encompass what you'll need in a higher category. But I'm surprised that it hasn't been studied yet.
Right. Yeah.
Yeah.
Any questions or comments? Well, I mean, your modeling of brain in terms of this hyperstructures is quite impressive. I mean, I should say, I mean,
Yes,
really interesting.
I think so. And you know, there is also a categorical approach to things in neuroscience done by André Eresman. I don't know if you know her.
I know the name, but I never met her.
Yes, she's a wife of Charles Eresman, and she has done a lot of interesting things that I must say I think have not been fully appreciated in the French mathematical community. So André Eresman's papers on yeah, actually she sort of uses limits instead, but she has some interesting ideas, and yeah. But you see, for example, here when I said assignments, I think it depends on very much both on the mathematical and other applications, because some of these assignments you are very close to being functors. But then, for example, should they preserve things like pullbacks and pushouts? Not necessarily. There are many situations where that wouldn't be good. And that also then makes the mathematics more complicated in a way.
I see. Yeah,
So,
very interesting.
I just wanted to sketch sort of a complex of ideas, and I'm not saying that this is a mathematical theory. I seen it as a presentation of a framework to be developed, both mathematically and applied.
Have you talked this with philosophers?
With who?
With philosophers? Philosophers.
No, not so much philosophers. No, I haven't really. In a way, I think maybe sociologists could be more interesting because this is the kind of structure that I think they are fighting with. I mean, societies of structures.
Right.
And I think, for example, as a metaphor, thinking in terms of a society is quite interesting. Even applying that to mathematics, how things interact and how levels are being created. And you see, when we form a society, that's exactly these levels I mentioned to you. And we form a group of, say, individuals, and then we form groups of groups, but we use the properties of each group to form the next group. That's really how a civilized society is being created.
I mean, it is like uh, one can maybe think Yone lemma as an object is how much defined via its relation with other objects, right? I mean,
Yes, yes.
so it is quite sociological in that sense.
Yeah, so in a way, I think even in mathematics, metaphors are from time to time quite useful. But you have to, of course, go back into the purely mathematical context and justify it there.
I mean, uh, recently I was preparing my lecture notes for uh, the algebraic geometry course that I will teach this semester, and I was looking at Yuri Manin's Introduction to Theory of Schemes. And
Mhm.
in that, there is a chapter on category theory, and what he says is that category theory is the sociology of mathematical objects.
Oh, I see. Oh, that's interesting. I haven't seen that. No. Oh, that's an interesting point of view. Yeah.
I
No,
mean,
no.
so I mean, really interesting. I mean, well, thank you very much. Any more questions or comments?
Maybe I have a comment.
Please.
There is this topos theoretical formulations in physics. Have you ever checked this direction? Maybe
I
this.
know about it, but I haven't really thought much about it. And yeah. I'm thinking about the British school of building quantum mechanics.
Uh-huh.
Talk why?
What? Sorry.
There's a British school. Is it Ingham that's
Yeah,
writing a
yeah, yeah, yeah. You're right.
yeah,
You're right.
yeah. I know about
I
it,
know.
but I must say I haven't studied it, so I could have an opinion about it. I didn't find it quite related to what
Mhm.
I was thinking about, but yeah. So my answer is really I don't know.
Yeah, yeah. I mean, I'm just because really kind of it has a suitable logical structure, especially the topos. I mean, to formalize quantum mechanics. I mean, it
Hmm.
somehow allows us to use, I mean, instead of a classical Boolean algebra stuff, it allows us to use, two things can be true at the same time. Somehow, this kind of
Hmm.
axioms can be included if you use topos instead of I mean, say,
Hmm.
or infinite topos.
Yeah, no,
I don't know, but
it may be quite interesting. And personally, I in physics, I recently been more challenged by this what I call higher order states in
uh-huh.
quantum mechanics and higher entanglement. And I think that these extensions of GHZ states, the Greenhorn-Seiliger states, actually, well, that's a prediction then, will be quite interesting in quantum computations, where you have sort of a wide variety of states and you build them up into more and more complicated states. And it has something to do, this is something I'm trying to understand at the moment. I think it's closely connected to what's called the Shaw code in Peter Shaw, who wrote one of these fundamental codes on quantum computers. And I think it's related to that. And I've had some contact with some physicists working on this, and yeah, but still that's work in progress.
Yeah, thank you.
Any more questions or comments? So let's thank our speaker, Nils, once more. Yeah. Thank you very much.
Okay, thank you very much. It was a pleasure to talk to you. And
it's our
let me
pleasure.
say, if some of you have some questions or comments afterwards or in a few days or so, don't hesitate to contact me and send me an email.
Okay, thank you. So we will meet 2 weeks from now, and our next speaker will be Professor Tan from National University of Singapore. He is head of the string theory group. He will talk on string theory and geometric Lagrange. Yeah.
Oh,
So the time will be different then because of the time difference of Singapore and Istanbul. It will be around noon time in Istanbul. So it will be 2 hours. So it will be around 10 o'clock in Trondheim.
okay, okay, very good. But please keep me on your list.
Yeah.
Yeah.
Okay,
Okay.
so see you all later.
Okay,
Bye-bye.
thank you so much. And then I click out. Yeah.
Yeah,
Okay. Bye.
bye. So we can stop
Well,
the